Are you struggling to build accurate AI models? Is the concept of supervised learning leaving you puzzled? Let's break it down to simple steps to make it easier to understand. Supervised learning is a fundamental approach in artificial intelligence that enables machines to learn from labeled data. It's the foundation for many practical AI applications we use daily. Let's dive into how supervised learning works and why it's crucial for building effective AI models. In supervised learning, we provide the algorithm with a dataset that includes both input features and their corresponding correct output labels. The goal is for the model to learn the relationship between these inputs and outputs, so it can make accurate predictions on new, unseen data. Imagine you're teaching a child to identify different types of fruits. You show them various fruits, telling them the name of each one. This is analogous to supervised learning. The fruits are the input data, and their names are the labels. As the child sees more examples, they learn to recognize and name fruits they haven't seen before. Similarly, in machine learning, we feed our algorithms numerous examples of input-output pairs. The algorithm then learns patterns and relationships within this data, forming a model that can generalize to new, unseen examples. Let's break down the supervised learning process into 8 steps. Data collection. The first step is gathering a large, diverse data set relevant to your problem. This data should include both input features and their corresponding correct output labels. Data pre-processing. Raw data often needs cleaning and formatting. This step involves handling missing values, normalizing data, and converting categorical variables into a format the algorithm can understand. Splitting the data. We typically divide our dataset into 3 parts: training, validation, and test sets. The training set is used to teach the model, the validation set helps in tuning the model's parameters, and the test set evaluates the final model's performance. Choosing a model. There are various supervised learning algorithms to choose from, such as linear regression, decision trees, random forests, support vector machines, and neural networks. The choice depends on the nature of your problem and data. Training the model. During this phase, the model learns from the training data. It adjusts its internal parameters to minimize the difference between its predictions and the actual labels. Validation. We use the validation set to fine-tune the model's hyperparameters and prevent overfitting. Overfitting occurs when a model learns the training data too well, including its noise and outliers, leading to poor generalization on new data. Testing. Once we're satisfied with the model's performance on the validation set, we evaluate it on the test set. This gives us an unbiased estimate of how well the model will perform on new, unseen data. Deployment and monitoring. After achieving satisfactory performance, we can deploy the model in a real-world setting. It's crucial to continually monitor its performance and retrain it periodically with new data. Supervised learning algorithms can be broadly categorized into 2 types: regression and classification. Regression algorithms predict continuous values. For example, predicting house prices based on features like size, location, and number of rooms. Common regression algorithms include linear regression, polynomial regression, and decision tree regression. Classification algorithms, on the other hand, predict discrete categories. This could be binary classification like spam detection in emails, or multi-class classification like identifying different species of flowers. Popular classification algorithms include logistic regression, decision trees, random forests, and support vector machines. While supervised learning is powerful, it's not without challenges. Data quality and quantity supervised learning requires large amounts of high-quality labeled data. Obtaining such data can be time-consuming and expensive. Overfitting models can sometimes learn the noise in the training data too well, leading to poor generalization on new data. Underfitting? Conversely, if a model is too simple, it may fail to capture the underlying patterns in the data. Bias in data. If the training data contains biases, the model will likely perpetuate these biases in its predictions. Computational resources. Training complex models on large data sets can require significant computational power and time. To address these challenges, researchers and practitioners employ various techniques. Data augmentation. This involves creating new training examples by applying transformations to existing data, effectively increasing the size and diversity of the training set. Transfer learning. Instead of training a model from scratch, we can use a pre-trained model and fine-tune it for our specific task. This is particularly useful when we have limited labeled data. Ensemble methods. Combining predictions from multiple models often leads to better performance and robustness than using a single model. Regularization techniques like L1, L2. Regularization help prevent overfitting by adding a penalty term to the loss function, discouraging the model from relying too heavily on any single feature. Cross-validation. This technique involves training and evaluating the model on different subsets of the data, providing a more robust estimate of the model's performance. As we look to the future, supervised learning continues to evolve. Some exciting developments include few-shot learning. This aims to train models that can learn from very few examples, mimicking human ability to quickly learn new concepts. Active learning. In this approach, the model actively queries the user for labels on the most informative examples, reducing the amount of labeled data needed. Federated learning. This allows training models on distributed data sets without centralizing the data, addressing privacy concerns in sensitive applications. Explainable AI. As AI models become more complex, there's a growing focus on making their decisions interpretable and explainable to humans. AutoML. Automated machine learning aims to automate the process of selecting and optimizing machine learning models, making AI more accessible to non-experts. Supervised learning is a cornerstone of modern AI, enabling machines to learn complex patterns from labeled data. As we've seen, it powers a wide range of applications across various industries. However, it's important to remember that supervised learning is just one approach in the broader field of machine learning. Other paradigms like unsupervised learning and reinforcement learning complement supervised learning, each with their own strengths and use cases. As you embark on your journey of building AI models, remember that the key to success lies in understanding your problem, choosing the right approach, and iterating based on results. Supervised learning provides a powerful framework for many tasks, but it's essential to stay curious and explore the full spectrum of machine learning techniques.
Thank you for watching. Join us for engaging topics, clear and concise explainers, and tutorials that will help you navigate the complexities of AI responsibly. We also believe in the power of community. Your questions, comments, and feedback are what make this journey exciting. So, don't hesitate to join the conversation and share your thoughts with us. Are you ready to embark on this journey towards a more ethical and responsible AI future? Hit that subscribe button and turn on notifications so you never miss an update. Together, let's shape the future of AI responsibly.